Okay, thank you all for joining back. We are moving to the last method for today, which is the secant method. So like I said previously, as the students rightly pointed out, for the Newton-Raphson method, you need to calculate the first derivative. So this is the Newton-Raphson method. You need to calculate the first derivative, but we don't want to do that. So we have to find a way to do that. And the way in which you calculate the first derivative is that you're going to use the backward difference. So remember in the second lecture, I think, we did numerical differentiation. So for numerical differentiation, we did the forward difference or the first finite difference, then we did the backward difference, then the centered difference. But in the second method, you are approximating the first derivative using the backward difference. The backward difference. So that means that you don't have to calculate the first derivative like you are doing in the Newton-Raphson method. For instance, now this is the backward difference formula. So in place of the first derivative, this is our Newton. This is the Newton-Raphson formula. So in place of the first derivative, you're replacing it with the backward difference formula. And we've already talked about the backward difference formula. If you are not sure of how we got this, just go back to the notes or to the recording. So we will derive this from Taylor's series. And this is the value of the function at the previous value of x. This is value of the function at the current value. And this is x at the previous value, and this is x at the current value. So in place of this, in place of having to calculate the first derivative, if you replace the first derivative with this, you're going to arrive at this. So this formula is called the secant method. It's just basically the Newton-Raphson method, but you are replacing the first derivative with the backward difference. And this is a graphical representation of this. So the backward difference is, this is the value of x at the previous value, and this is value of x at the current value. So we've already talked about that. So this is the secant method. And looking at the secant method, you don't need to calculate the first derivative. All you just need to know is you need to know the value of the function at this current step size. Then you know the value of the function at the previous step size. Then you know this, and you pretty much estimate the roots using that. So this is the secant method. And looking at it, remember for the previous method, we just needed one guess, but now we need two guesses. We need the guess at this particular value, then we need the guess at this particular value. So for the secant method, it eliminates the need for you to find the derivative, but the implication of that is that you need two guesses now. You're going to be giving two guesses or two estimates. So let's go to the same example, but now we have two guesses. So x minus 1 is this, and x when I is 0 is this. So that's the secant method. Like I said, the secant method is the same thing as the Newton-Raphson method. It's just that you don't need to calculate the first derivative. And the implication of that is that you need two estimates now. You need to evaluate this function at this value. Then you need to evaluate the function at this value. So we are going to use the secant method in order to estimate the root of this function. So we are given this at x minus 1. We said that is equal to 0. Then at x of 0 is equal to 1. So based on the secant method, you need to calculate this function and also this function. So the value of the function at x minus 1 is given by this. So this is the function. So in place of, you're evaluating the function at x minus 1. So in place of x minus 1, you put 0 because x minus 1 is 0. So you put 0 here, you put 0 here. And you arrive at the value of the function at x minus 1. Then you evaluate the function at x of 0. So we know that x of 0 is 1. So you're going to put 1 here. I'm going to put 1 here. After you've done that, you're going to evaluate, or you're going to estimate the root because you already have all you need. So this is x naught, which is 1. Then this is f of x minus 1, which is 1. And it is fx of x naught, which is this. So you already have all you need. Then you estimate the value of the root. You're going to track the estimated error. You're going to track the true error. So for the second iteration, for the first iteration, remember you were given this and you were given this. So for the next iteration is x0 and x1. Is x0 and x1. So for the next iteration is x0 and x1. So x0, you're giving in the question. Then x1 is what you calculated here. So you evaluate the function at x0. Then you evaluate the function at x1. Then you arrive at this. Then you would evaluate the roots at x2 using this formula. So you already have everything you need. Then we arrived at this. You track the estimated error and the true error. You go to the next iteration. In the next iteration is x1 and x2 now. The next iteration is x1 and x2. So you evaluate, you know x1 from previously. We have x1 already. This is x1. Then x2, we calculated x2 here. So you evaluate the function at x1, you evaluate the function at x2. We got this and this. Then we'll substitute it into the secant method, into the secant formula to arrive at this x3. Then we'll keep track of the error. This is the estimate error and this is the true error. So for the fourth iteration, what you need x2. So we already know x2. You need x2. Then you need x3. And we got x3 as 0.56 is equal to 0.5671. So similarly, you're going to evaluate the function at x2, then you evaluate the function at x3. And after that, you substitute into the secant method to get x4. So you get x4. You get x4. So for the fifth iteration, can somebody tell me what you need for the fifth iteration? So just type it in the chat. So what do you need for the fifth iteration? So remember for the first iteration, okay, I think I have an answer. Yes, you need x3 and x4. So thank you for that. So for the fourth iteration, for the fifth iteration, sorry, you need x3 and x4. You need x3, then you need x4. Then you calculate, you get x5, get x5. So for the fifth iteration, for the sixth iteration, you keep on going on and on like that. So this is how this is the second method. You keep on going on and on like that. And like I said, you keep track of the error at each iteration. You keep track of the uh, error. So if you look at this is the second method that we are just considering now. And this is the first position method. We did the first position method last week. If you look at it, it looks similar. It looks very, very similar. Like this is the root, estimated root. This is the next value of the root. This is the upper limit. This is the value of x at the previous iteration. Then you evaluate this, you have this lower limit, upper limit. This is the previous value, this is the current value. So they are similar on a time by time basis. So the next question you'll be asking now is that, what's the difference? And the difference is that for the first position method, the lower limits and the upper limits, the root is a bracketing method. So the root should be between the lower limit and the upper limit. But for the second method, these values is not necessarily going to be this value and this value is not necessarily going to be within the root. Okay, let me say it clearly now. For the first position method, you are very sure that the root is located between the lower limit and between the upper limit. You are so sure. But for the second method, this and these values and this value, you are not, is not certain that the root is actually between these two values. In order to explain better, let me go back to the figure of the second method. Okay, look at, this is the second method, right? And this is the true value of the root. Remember, it is when the root is when the function touches the x-axis. But now, this is the second method. This is xi minus 1, and this is xi. Normally, for the first position method, the lower limit should be here, then the upper limit should be here. Then the root is between the lower limit and the upper limit. But look at this representation. This value and this value, like the root is not between these two limits. In fact, the root is outside of the limits, is not within xi minus 1 and xi, is outside this bracket. But in the first position method, we are sure that there should be a lower limit here and there should be an upper limit here. So you are sure that the root is between those two brackets. But for the first, for the first position method, you have a lower limit and you have an upper limit. And you are sure that the root is between the lower limit and the upper limit. But for the second method, you have, this is like the lower limit and this is like the upper limit, but it's not guaranteed that the root is between these two values. Like from this representation, The root is actually outside of the two limits. It's actually here. So that is basically the difference. Then in order to really bring out the difference, we are going to use an example in which we are going to find the root using the first position method and the secant method, so that we want to be very sure of the difference. So this example is just to show the difference between the first position method and the secant method. So yeah, we are saying that the lower limit and xi minus 1 should be 0.5, and the upper limit or xi should be 5, should be 5.0. So using the first position method now, so we're going to use the first position method first, then we use the second method. So this is your lower limit and this is your upper limit. The lower limit is 0.5, then the upper limit is 5. So in order to get xr, you just use the formula, which is this. So you substitute the lower limit with the upper limit. Then this is the evaluation of the function at the upper limit. And this is the evaluation of the function at the lower limit. Evaluation of the function at the upper limit. So when you do that, you arrive at 1.8. Then remember when we're doing the first position method, after arriving at this value of xr, then you are going to evaluate, okay, let me write it here. You're going to evaluate f of xl, then you evaluate f of xr. Then you evaluate f of xr. So this is the first position method. So after doing this for the first position method, if you can remember, you're going to evaluate this. So if you evaluate this and this is less than 0, and this is less than 0, you replace the upper limit. So if this evaluation, if it's less than 0, then you replace the upper limit with xr, So I skipped this evaluation. So we're supposed to evaluate at, let me just write it here. So you're supposed to evaluate at the function at this value. Then you evaluate the function at the lower limit, and the lower limit is 0.5. Then if this evaluation, when you multiply this together, if it's less than 0, you replace the upper limit with the root you just calculated. So I skipped that step. So if you do this evaluation, it's going to be a negative number, less than 0. So that means that we replace the upper limit in the next iteration. Replace the upper limit, which is xu, with xr, with this xr we just calculated. So this is now your lower limit and this is now your upper limit. Then you evaluate this function. We arrive at this. So the next thing is to do this evaluation. So you evaluate f at the root you just calculated. Then you evaluate it at the lower limit. So the lower limit is 0.5. 0.5. So after doing this evaluation here, you're going to test If it is less than 0, you're going to replace the upper limit with XR, with this new XR you've calculated. But if it's greater than 0, is the lower limit. So if it is less than 0, you replace the upper limit with XR. Then if it is greater than 0, then you replace the lower limit now with XR. So yeah, if you do this evaluation, you will see that it's less than 0. Sorry, I didn't do it. I just skipped that step. If you do this evaluation, you will see that, so after the class, you can just try it for yourself. You will see that it's less than 0. And since it's less than 0, you are going to replace the upper limit with XR. So we are replacing the upper limit with XR, and this is the XR we just calculated. Then we are leaving the lower limit. So you keep on doing that. Now you have a new root. So the next thing for you to do is to evaluate the function at the new root. Then you evaluate the function at the lower limit, which is 0.5. If it is less than 0, you replace the upper limit with this root. But if it is greater than 0, you're going to replace the lower limits with the value of the root you just calculated. So this is the first position method. We did it last week, and this is how it goes. But if you are going to use the secant method, remember the question is to compare the secant method with the first position method. If we were to go by the secant method, this is what you have. So you evaluate, this is the equation. Let me just bring it down again. This is the equation for the secant method. So for the first iteration, you're going to evaluate x1. You evaluate x1. You're evaluating x1 at the first iteration. Then this is x0. Then this is x0. Then this is x minus 1. This is x0. Okay, this is x0. And this is x minus 1. And this is x0. So for x1, you evaluate this. So when we did the evaluation, so this is the evaluation here. So the 5 is x0, because this is x minus 1. For the first iteration, this is x minus 1, and this is x0. So you evaluate this, you got this. Then you already have x1, right? You already have x1. So for the next iteration, which is the second iteration, the equation, you're going to evaluate x2 now. Control C. So you're going to evaluate x2. So you change the value. Here is 2, and here is 1. Here is 1, and here is 0. Here is 1. Here is 0. And here is 1. So this is the evaluation now. You're going to get a new value. Then for the third iteration, so you keep on doing it like that. So if you look at the difference now, so for the secant method, for the first iteration, you get x1, and you know x naught. You get x1. Let me just write it here. You get x1. Then you know x0 and x minus 1. That's for the first iteration. So for the second iteration, you get x2. You get x2. Then you know x1 and x0. So you keep on doing it like that. That's for the second iteration. Then for the third iteration, you get x3. Then you know x2 and x1. So this is the secant method. And if you can immediately spot the difference. For the first position method, you have to do this evaluation. And if it's less than 0, you have to replace the upper limit with the root. And if it's greater than 0, you replace the lower limit with the root. But in the secant method, we are not doing any if statements. We don't need this evaluation. Everything is happening sequentially. So the first iteration, we get x1, and we know this and this. For the second iteration, we get x2, we know this and this. For the third iteration, we get x3, we know this and this. So we don't need to be testing for any condition in the first position method. We don't need to be testing for any kind of condition. For the first position method, we had to test for this condition in order to replace the lower limit and the upper or the upper limit. But in the second method, we don't even have any condition. All you just need to do is just to follow this sequence. And it's because of this, that's why the secant method can actually diverge. The roots can actually diverge, like what we saw in the Newton-Raphson method. The error was escalating and increasing. The second method is faster. Yes, yes, John, thank you for that observation. The second method is really, really fast. And the reason why it's fast is because you don't need to do any evaluation. You don't need to do this evaluation to test for this condition, then having to replace the lower limit or the upper limit. But this, for the second method, is just sequentially. You're not, you are not, um, you are not bothered if the root is bracketed. So it's an open method. That's why we call it open method. Remember that this topic is open method for finding the roots. In the previous class, we did bracketing method. So the limits should be bracketed. The upper limit and the lower limit should be bracketed. But in the open method, first of all, what I want you to take home is that in the open method, it's just one guess you have. Like for the case of the fixed point iteration and the Newton-Raphson method, it's just one guess you had for fixed point iteration. Then for the Newton-Raphson method, is also one guess we had. It's just one guess you'll be giving. So you will not be giving like a lower limit or the upper limit. Then the second method, you are giving a limit, right? But it's not a bracketing method in that the limits you are giving, so we are giving this limit and this limit. The limit you are giving doesn't necessarily bracket the roots. In fact, it can, is these two limits we are giving is not within, it doesn't bracket the roots because the root is here and this was the limit we were giving. So that's the reason why it could diverge. And that was the reason why the Newton-Raphson method, it was, the error was increasing, was like escalating because the Newton-Raphson method is fast and the second method is fast. But the problem with it is that it diverges because this root, this estimate you are giving is not, most of the time, is not within the true root. So it's outside of the true root. So it could diverge, but eventually with time and with by you increasing the number of iterations, it's still going to eventually converge. So um, that is the difference. So I want you to note the difference between the secant method and the first position method, because though they look alike actually, they look alike and they are very similar, but they are very different. They are very different, and I hope you understand the difference now. So this is the end of the lecture for today. In the next class, we are going to be concluding roots. So this is the second lecture on finding the roots of equation. So by next week, hopefully, we are going to conclude the discussion on the roots of the equation. So you have a question, John. So if you have a question, just type it in the chat, then I would look at it and try to answer. So I'm just summarizing now. So last class we talked about bracketing methods. In bracketing method, you are going to you are given two guesses, and the roots, you are sure that the root is in between those two guesses. But in the open method, you are given just one guess. And in the case where you are giving one guess, and in the case where you are giving two guesses, like the secant method, the guesses you are giving do not necessarily bracket the root. So the guesses, you are not even sure, and you're not even certain if the root is between those two guesses you are giving in the secant method. Okay, can that happen in the case of the secant method, where it behaves abnormal sometimes, where you do more iteration, or because of the replacement of the derivative, it doesn't behave abnormal? Okay, if I understand your question, the the Newton-Raphson method and the secant method they're pretty much the same thing. The Newton-Raphson method, like we see, it suffers from divergence. So it could diverge. The root could diverge. So that's like a major pitfall. That's the downfall of the Newton-Raphson method. Also, the secant method could diverge. It also suffers from divergence. It also suffers from divergence. But the bracketing methods we considered last week, they don't suffer from that. They converge. Like the the first position method, the first position method, the first position method, and the bisect method, the both of them, or the bisection method, the both of them, they don't suffer from divergence. They will definitely converge. They converge, and the bisection method too converges, but they are very slow, very, very slow. And the reason why they are very slow is that you have to evaluate a condition, and you want to be very sure that it doesn't diverge, because for every iteration, the lower limit and the upper limit, the root is within the lower limit and the upper limit. That's for these two methods. But for these two methods, you don't, that condition doesn't exist. So that makes it very, very fast. But the disadvantage is that it diverges, but then it's going to eventually converge. Like the example we did, the error was like we're getting 5,000%, 2,000% error, but with more iteration, it would eventually converge. So that's the open that's the open method for finding the root. So you should know the difference. Then before we close, I just want to just give you something like an expo really. So this is the equation, this is the code for for the fixed point iteration method. And this is the code for the Newton-Raphson method. And they are basically the same thing. It's just that this line is the difference, but I didn't give you the code for the secant method. The code for the secant method is missing. So I'm encouraging you to try to write the code for the secant method. It's not difficult. It's not difficult. It's not an assignment. It's just something that can probably come out in the exam because I did not give you. So that means that I want you to write the code yourself. So anything I did not give you in the notes, and that means that I want you to do it yourself. So it's not an assignment, and don't come back with me that I tried it, it didn't work. I'm telling you to do it on your own and just keep trying. All of you just come together, and if it doesn't work, don't get back to me that it's something is not working or something. Just try it and come up with the code yourself. So like I said, what I did not give you in the notes is definitely in the exam. All these things are in the notes, won't come out. Is what is not in the notes that will come out. So my advice for you is that you should try to um, write the code for the secant method and see that is the correct code and it's working. And please don't get back to me with any code you come up with. Just do it on your own and verify yourself that it's working properly. So this is the end of the class. So I'll be stopping the meeting